part 2 of the fundamental theorem of calculus, which honestly is the most exciting part for you properly. So evaluate the following integral using part 2 of the fundamental theorem of calculus. Tells me that the definite integral from a to b of f of x dx is equal to this antiderivative evaluated at those limits. So what's the derivative and the derivative of the cube root of x will? Let's first rewrite it. This definite integral from 1 to 8 is the x to the 1 over 3 power dx. So if I anti-differentiate, I'm going to increase the exponent by 1. So it is gonna because x to the 4 over 3, and then I'm divided by the new exponent. So I multiply by 3 over 4, and have evaluated this antiderivative at the upper limit minus the antiderivative evaluated at the lower limits. It is a way to write this out properly is as follows. So pay attention. I'm going to draw straight line, lower limit at the bottom, upper limit at the top. You don't write dx anymore because you already took the antiderivative and you don't write the integral sign anymore. Okay, so this sign and the dx are a package deal. You don't write them anymore. Now you write out the line on the right with the lower limit and the upper limits, meaning I already took the antiderivative. I am going to evaluate them at these values. Always substitute in upper limits first minus the lower limits. Let's leave the 3 over 4 out of the picture. I am going to have 8 to the 4 over 3 minus 1 to the 4 over 3. The 4 of 3, okay, so this is gonna be 4, 8 to the 8 4, that is the cube root of 8, right? You take the denominator, take that root of the number, so that 2, and then raise it to 4th power, so that p16 minus, and then 1 raised to any thing is 1. So nice. Okay, so this be 3 times 15 over 4, which is 45 over 4. Next example, we have the definite integral from 0 to 2 of y minus 1 times 2y plus 1 dy. I am not ready to antiderivative differentiation just yet, so I want to multiply out my integral, right? This expression here. So I have integral from 0 to 2. This is going to be 2 squared plus minus 2y, that minus y minus 1 dy. All right, you must write dy every single step of the way until you anti-differentiate. So if there an integral sign, there better be a d, whatever in this case dy. Here we go term by term. Antiderivative of 2y squared is going to be 2 over 3y cubed. Antiderivative of negative y is negative y over 2y squared, and antiderivative of negative 1 is just negative y. Already took my antiderivative, so now I am going to evaluate it from 0 to 2. All right, substituting in the upper limit first, I am going to have 2 over 3 times 2 cube minus 1 over half times 2 squared minus 2. It is minus, and then if 1 substitute in 0, I get 0 for all of the terms. So I'm going to be left with 16 over 3 minus 1 over half times 2 squared is 2. Minus 2, so that going to be 16 over 3 minus 6 over 3 minus 6 minus another 6 over 3. So I am just left with 4 over 3. Let us look at another example. Are you having fun? So we have the integral from 0 to 1 of 10 to the x dx. So this one you can just start anti-differentiating, writing away. You remember antiderivative of 10 to the x. Just think to yourself, if it is to the x, it is e to the x, since it is not either. The x you got divided by ln over whatever the basis. So antiderivative is b10 to the x over ln over 10, and then I'm going to evaluate this from 0 to 1. So I have always like to just leave this constant outside. I'm just write 1 over ln over 10, then I have 10 to the 1 first minus 10 to the 0. Well, 10 to the first is the 10 to the 0 is 1, so is P9. So I have 9 over natural log of 10. One more, I have the integral from 1 to 2 of 4 plus u squared over u cubed du. Well, first we have got to get it an integral friendly from right, so we can differentiate term by term. So I notice the denominator has just one term, which means I can rewrite it under each of the terms in the numerator. So I am going with write 4 over u cubed plus u squared over cube u cubed du, and then going rewrite these terms so I can clearly identify the exponents. So this is for u to the negative third plus 1 over u, which is u to the negative first, or you can leave it 1 over u, right? Perhaps you thinking ahead. All right, I am not write the integral sign anymore. It is time to anti-differentiate. So antiderivatives of 4u to the negative third, I'm going to increase the exponent by 1. So it is going to be come u to the negative second. I still have that 4. I have to divide by my new exponent, which what is the antiderivative of u to negative first. You can't add it 1 and divide it by the new exponent. On what is that? Do you remember? It is good. All natural along of absolute value of u. Looks good. And then I evaluate all of this from 1 to 2. All right, now this is basically a negative 2. Write u to the negative second. So I am going to have for the upper limits negative 2 times 2 to the negative second plus natural log over 2. When I substitute in the upper limit minus negative 2 times 1 to the negative second plus natural log of 1. All right, what are we left with here? So this is a negative 2 over 2 squared. So negative 2 over 4 plus ln of 2. And then this is going to turn into negative 2 plus 0, right? Ln of 1 is 0. So I just have negative 1/2 plus ln over 2 plus 2, which give me 3 halves plus ln over 2 of 2. Last example, the most exciting ones of the lesson. Perhaps find g of x, g prime of x, if g of equals the integral from tan x to x square over 1, the square root of 2 plus t to the fourth dt. So it looks like it is time to use good old fundamental theorem calculus. A big problem, neither of my limits of integration is a constant. What to do? So I am going to first start off rewriting things. So I have g prime x. Remember that p derivative with respect to x of the integral from tan x to x square of 1 over 1. The square root of 2 plus t to the fourth dt. Alright, I need to introduce a constant, and what I am going to do is break up my integral at 0. You can break it up pretty much anywhere you want because any number will work. So I'm going to write this as the integral from 10x to 0 of 1 over square root over 2 plus t to the fourth dt plus, and then you just have to pick up where you left off. So if you split it some more other than 0, just make square this number and this limit match up until x squared of 1 over square root over 2 of 2 plus t to the fourth dt. Why I am allowed to do this? Well, this was one of the properties that cover in the previous lesson of our integral, that we are allowed to break up the sum as long as we pick back up right where we left off. Okay, well, things are looking better. I am already very happy with this integral because I can just apply the theorem of calculus. This one, however, the first one, remember, I need the lower limit to be constant. So what I can do you remember how in that previous problem we flipped the limits of integration? Just anytime you flip the limits of integration, remember you need to add negative sign. So we have 0 to tan x, 1 over r added 2 plus t to the fourth dt, but that negative sitting outside plus. Integral 0 to the square 1 over square root 2 plus t to the fourth dt. Now we are ready to rule. So when I take the derivative, remember I am just gonna substitute the upper limits in for the variable here. So I am going to have to forget your negative 1 over square root over 2 plus this is b tangent to the fourth x times, and then do not forget I need to apply the chain rule. So I need to multiply by the derivative of tangent of x, which is the second square. Do so. Our first ones does done, plus now I am going to substitute in the x square for t. So I'm going to have 1 over the square root of 2 plus x square raised to the fourth is going to be x to the 8th, and then change rule. What do I need to multiply by that? Write 2x, good, and then to the clean things up, just put each of these little guys in the numerator, so it looks so nice. Let's put the positive one first. Who likes a negative as your leading term? It is not so up. So we will have 2x over rad 2 plus x to the 8th minus seconds square x over the square root of 2 plus 10x to the 4th, and that is our final answer.